Hey crazies, electronics are pretty amazing. Indoor lighting, computers, phones, calculators, televisions, hearing aids, but none of that would be possible without electric current. It's kind of the life essence of electronics. And every school kid knows that current takes the path of least resistance, right? Well, that rule is actually kinda wrong. Okay, to be fair, it's not 100% wrong. Maybe more like 50%? It could use some improvement, is what I'm saying. Maybe we should start with a demonstration. Experiment clone! Your time has come!
Okay, you talk, I work?
That's the plan.
Okay. Switch on.
One of your light bulbs isn't bulbing.
Well.
No. It's causing it to spark.
Here's a relatively simple circuit. All these light bulbs are connected by wires on both sides. The circuit diagram would look something like this. There's also a multimeter, so we can measure any electric current we want. These bulbs have different wattage ratings, which means they have different resistances. If the current takes the path of least resistance, we'd expect it to pass through this bulb. So let's measure the electric current in each bulb and see what happens. As we can see, the current did take the path of least resistance, but it also took every other path. It took every closed path that was available. And that makes perfect sense if you think about it. If water was flowing slowly and steadily down a stream, but encountered a split, you wouldn't expect the water to only take the bigger path. It's gonna take both. The same thing happens with electric current in a circuit. If there's a path it can take, it's gonna take it. It went through every available path in this circuit. It just didn't do that in equal amounts. There's more current in the paths with less resistance. So let's try rewriting this rule. Current takes the path of least resistance? Incorrect. More current takes the path of less resistance, but some current takes each and every path. It's not nearly as catchy as the original, but at least it's correct. Maybe an acronym? Fuller Biscuitape.
Nailed it.
Nope, never mind. Where was I? Oh, right. To understand this rule, we need to dig a little deeper. Electric current, or just current for short, is the flow of electric charge. You can imagine a bunch of tiny balls, or some kind of fluid. Neither is 100% accurate, but they're both good enough for today. This charge does obey certain rules, fundamental rules, like the conservation of charge. In science, conservation just means keeping things the same, so conservation of charge just means the amount of charge stays the same. Conservation of electric charge shall not be violated! And no exceptions this time, because quantum mechanics. Seriously, I did a whole video on it if you can handle some math. Speaking of math, here's the conservation of charge. Yes, I know that can look a little overwhelming if you've never seen anything like this before. Perfectly normal reaction. But I'm gonna explain every little individual piece, and we're gonna visualize them as we go, so it'll make sense by the time I'm done. Okay, so this Greek letter rho is charge density. That's how closely packed the charge is. If it's tightly packed, then the density is big. If it's loosely packed, the density is low. This T on the bottom stands for time, which means this whole fraction is how density changes in time. If the density isn't changing, the fraction is 0. If the density is going up, the fraction is positive. If the density is going down, the fraction is negative. Not so bad so far, right? We all kinda understand how density works. Next, this triangle right here means changes in space. When that triangle is followed by a dot, we're only concerned with into and out of a space. For all you math nerds out there, we're talking about divergence. The J is the electric current. Remember, that's just the flow of electric charge. That means this whole thing tells us how much charge is moving into or out of a space. Visually, let's imagine a sphere enclosing a volume of space. If charge is flowing into the sphere, we get a negative number. If charge is flowing out of the sphere, we get a positive number. If just as much charge flows in as flows out, we get a 0 answer. Now let's put it all together. All this equation says is that if charge is getting more or less dense in one spot over time, then that's because charge flowed into or out of that spot. Seriously, that's it. That's all it says. Electric charge can't be created or destroyed, so we know any change in density is the result of a flow. And that flow is how all electronics work. That's why we call it electronics. They're based on the flow of electrons. Circuit design is all about predicting where this electric current will go. Back in 1845, a guy by the name of Gustav Kirchhoff based one of his circuit laws on this principle of charge conservation. But he made one more assumption. So what's this extra assumption he made? That the electric current is very well behaved. He assumed that every part of a circuit has a consistent amount of charge. It's not gonna bunch up anywhere or pop out of the circuit. The flow is nice and steady. To put this in terms of what we were just talking about, he assumed the charge density doesn't change. How accurate is that? Well, pretty accurate actually. I mean, it's not always true. Off the top of my head, high voltage long distance lines are an exception. The charge actually bunches up and spreads out in a kind of wavy pattern. But that's an extreme case. For ordinary everyday electronics, steady current is a reasonable assumption. And that leaves us with just the flow term in the conservation of charge. The total flow into or out of a volume is 0. Or better yet, the flow into a volume equals the flow out of that volume. Since electric current is that flow, we can say the current in equals the current out. That's Kirchhoff's current law, or Kirchhoff's junction rule as I like to call it. It goes by a lot of names. What's a junction? It's kind of like a fork in the road. You mean like this? No, not literally a fork in the road. It's a metaphor. It's just a visual analog. See, it kind of looks like the prongs of a fork. Anytime there are 3 or more wires coming together at a single point, we call it a junction. Say there's an imaginary sphere surrounding a junction. No matter what, the current entering that sphere must equal the current that exits. We know that because of Kirchhoff's junction rule. Technically, it applies everywhere, including the middle of a straight wire. That just isn't very interesting. We don't actually need the rule unless there's a junction. If a single charge comes across a junction, it has to make a choice. Which path does it take? We don't know what each individual charge will do in that situation. It's random, but not equally random. We do notice some patterns when we look at what a bunch of charges will do. Remember, more current takes the path of less resistance, but some current takes each and every path. If we know the resistances of each path, we can make a prediction about how much current will go that way. More resistance means less current, and vice versa. As you can see, the new rule matches our experiment really well. Just remember, every path is going to have some current in it, including birds on power lines. Power lines are not insulated, so even though they have less resistance than the bird, there is a little current passing through that bird. I wonder what that feels like. How shocking was this news about the current rule? Let us know in the comments. Thanks for liking and sharing this video. A special thanks goes out to all my Patreon patrons and YouTube members for making all this possible. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy.
We're done now, right? I can stop working?
Yep. Okay, cool. Oscar said he would have been happier if we had mentioned the word mass at least once in the last video. I was trying to keep the video focused on weight versus normal force. Mass isn't even a force, so it can't be measured on a force scale. Although, based on the bad comments I've been getting, maybe that was a mistake. Anyway, thanks for watching.